I like to talk about not just the history of geology, but very much the future of geology. Because all those wonderful ideas and laws that the fathers of geology came up with can be applied just as easily forward in time as they can backwards in time. And you know, anything that predicts the future, that's pretty exciting stuff there. So, today we're going to talk about the geology of Bryce and this larger region we call the Grand Staircase. And all these different layers record huge amounts of Earth history. If you think of layers in rock like chapters in this gigantic, textbook that is the story of planet Earth, this is the only unabridged version, the one right here that you find at the Grand Staircase. Because in fact, we have 600 million years of Earth history recorded. From the very bottom layers in the Grand Canyon, it's continuous all the way up here to Bryce. Now, I could actually tell you the whole story of the Grand Staircase, and I think if I was moving quickly and well organized, I could do it in about 40 hours. I mean, that's pretty good. 600 million years, we're used to 40 hours, that's not bad. But I know we've only got a little bit of time. So I'm only going to talk about 2 rocks in the entirety of the Grand Staircase. The most interesting rocks, of course, the most interesting 2. And as luck would have it, the most interesting 2 rocks in the entire Grand Staircase are the ones that are here at Bryce, the lofty summit of the Grand Staircase. Okay. My name is Ranger Poe, and why I studied geology in college is to become a paleoclimatologist. Are there any registered Utah voters by chance? Just a couple. Okay. Usually, if there was a lot of Utahns in the audience, I would say I'm an Earth historian. Because that's a lot more palatable than using words like climate and climatology. But there's only 2 of them. They seem very friendly. So I'm going to say I'm a paleoclimatologist today. That means that in studying these 2 rocks, the most interesting 2 of the Grand Staircase, we can learn a lot about our past and also our future. This is the 2 in question. Can you identify them? Would you recognize what this black one is by chance? Basalt's a good guess until I let you hold it. It's not very heavy. In fact, it's very light. It's not quite pumice. It's not even a volcanic rock. I'll start it on this end because the gentleman was brave enough to make the first guess there. Now, what do you think? Coal. It is. It's exactly right. It's almost anthracite. Okay, and there's a fellow who knows his coal. It's the coal we have in Utah is of pretty good high quality. It's not quite as nice as the stuff in West Virginia or maybe Pennsylvania, but it's a near anthracite grade coal. What's this rock here, would you suppose? This is the rock of Bryce Canyon, but what rock type?
Sandstone?
Sandstone's a good guess. Dolomite's pretty close, interestingly enough. It's a limestone. One thing you should understand is these 2 rocks have a lot in common. And that's why I call this presentation a tale of 2 rocks. We've got the limestone here and the coal. Both have a lot of carbon in them. Where does the coal come from? What did the coal used to be?
Fossil.
Plants. Yeah, plant material. Trees, mostly. But a lot of plant material. That's where all that carbon came from. What did limestone used to be? I'll go ahead and pass this around now, too. Yeah, it's marine creatures. Seashells, little tiny diatoms, all these different creatures that live in the ocean. When they die, they leave their calcium carbonate skeleton or bones. It's not really bones, but they leave all that behind, and that makes a limestone deposit. So both of these rocks were once living things. It makes them kind of special. We call that they're biogenic in origin. But now, let me ask some more interesting questions, maybe kind of modern-day stuff people are interested in. Which one of these 2 rocks do you think is more valuable? The coal or the limestone?
The coal.
The coal, right. Okay, well, $85 a ton. That's what it costs to get Utah coal. The cruddy stuff in Wyoming is about $65 a ton. But, we got some pretty good stuff, so it sells for $85. That piece of limestone that's still going around, you certainly couldn't take one from the national park here, but from a rock shop, maybe out by Ruby's Inn, someplace where they've legally obtained the rock from Forest Service land or somewhere else, they would probably sell you that 1-pound piece of rock for about $10. So $10 a pound or $85 a ton. Now, see, an economist would go, yeah, but it's not about price point, it's about volume of sale, okay? And so how much coal do you sell versus the limestone? Hey, we sell barely a ton of limestone, probably from all the rock shops combined, but 25 million tons of coal. So you do the math on that one, you get like $2 billion profit from the coal. But now a politician would tell you that the easiest way to reduce economics is to jobs. That's all that really matters. And then you don't even need a degree. It's just really simple. Jobs, all about jobs. So in the state of Utah, for extracting coal, it employs 1,900 people. It's quite a few. The limestone rock of Bryce Canyon is important to the tourism economy of this immediate area. Now, of the entire state of Utah, the tourism economy is about a $7.9 billion industry. So coal, $2 billion, 7.9. But it works out that not everybody who visits Utah comes to Bryce Canyon. What percentage would you guess actually makes it to Bryce? Anybody has
40.
to guess? 40? That's a little bit less. Actually, quite a bit less.
20.
15.
15 is 10%. 10%. Can you believe that? Only 10% of the people that come to Utah, yeah, they come to Bryce. So if we were to focus on the economy of just this immediate area, we might choose Garfield County, because that's the county we're in. It's 5,000 square miles. It's a big county. Only has 5,000 square people living in it. You know, so for the math majors, the squares cancel out. They just have one person per, yeah, thank you for smiling. It's one of my better jokes, you know, maybe it's raining. Jobs in the tourism economy, all relating to the limestone of Bryce. So we've got 1,900 for the entire state, 1,700 for, you know, this immediate area, one county of the entire state. All right, well, with that kind of information, then here's the next question, for this might be the most important of all. Which one of these two rocks, and it is one of these two, but which one of these two rocks is the state rock of Utah? What would you guess? How many would say limestone, the Bryce Canyon limestone? All right, and how many coal?
Utah.
Yeah, it's coal. Can you imagine? Of all the beautiful rocks we have in Utah, this is our essence that we want to put forward to the world. Woohoo! Come to Utah and see our coal.
Needs to be changed.
Yeah. How many registered Utah voters again? Yeah, see, it's going to take a lot more. But maybe someday we could make this the state rock. And that would be so good for our visitation. We might go to 11 or 12%, you know, instead of just 10. Wouldn't that be great? Okay, so now we begin the geologic story of these rocks. I'm going to start with the oldest rock, which is in fact the coal. And coal forms in swampy wetlands. And so you might be thinking, wow, how do you get swampy wetlands in a place like Utah? Well, going back to the Cretaceous time period, this is what the lay of the land was. And these maps, these are what we call paleo-environmental indicator maps. Basically, all the best paleontology, geology, climatology comes together to produce what we think the land used to look like. So if you were to start by looking at the whole of North America here, right away you can see there's a problem. There's a great big ocean arm coming right through the middle here. This would be where the Rocky Mountains will eventually form, but without them we have ocean. Because what I want you to focus on is the red star here, because of course that's where Bryce Canyon would be. So if we go back that far, we're on the edge of an ocean. Tropical rainforest jungle. Great big Amazon-like rivers flowing through it out into the ocean. How do you get an ocean up on the continent? Easy. Global warming. Okay? But it was different back then. It wasn't like the dinosaurs, you know, as you see them here. They weren't driving sport utility vehicles to their commutes to work, you know. They weren't getting their electricity from coal-fired electric plants. It was a whole bunch of different problems back then that mostly had to deal with volcanism. The amount of volcanic activity in the Cretaceous was a lot more pronounced than it is today. Back then, the volcanoes were spewing out about 500 million tons of carbon dioxide every single year. 500 million tons. Which seems like a lot until I tell you factually that humanity produces 30 billion metric tons each year now, 60 times more than our greatest point of volcanism. But it took a few million years at that rate to be able to get oceans up on top of the continent. You know, who knows how long it'll take in our future. Nevertheless, with oceans here, all these gigantic jungle-type trees are falling into the rivers. They're being washed in these swampy wetlands, and they're ended up getting buried. And that's how you make coal. You have to bury that plant material pretty quickly, because if oxygen can reach it, when it oxidizes, basically, it decomposes. The tree becomes carbon dioxide eventually. It ends up back in the atmosphere. But if you bury it, you can preserve it. And I'm glad to see some junior rangers showing up here. You guys want to help me? Yeah? Okay. I need some help explaining to everybody else why coal is so important, ecologically speaking. Because what coal does is it filters water. And some of you probably knew this, because what do you have in your water filter at home? What's the active ingredient? Charcoal. Exactly, a pure form of coal. So coming out of these rivers, as always has and always will be, is all kinds of heavy metals flowing out of mountains. But when they get to these swampy wetlands, you know, where the dinosaurs and stuff are swimming around, well, the coal is going to absorb all those heavy metals. And that's what you guys are going to help me with. You're going to be these kinds of poisons. Are you up for being poisoned today? Okay. I love to see those smiles. All right, so we're going to tell these folks a little bit about each one. I'm going to have you hold them up so they can all see. All right? So we're going to start with selenium. Selenium is, well, I should explain one thing. Inside parentheses here, this is the amount that's permissible by the American law, by the United States, the Government Clean Air Act, to come in the smoke, the fly ash that comes out of coal plants. It's considered safe as long as the amount of selenium doesn't exceed 7.7 parts per million. Now what selenium does is causes hair loss, kidney failure, and lung failure. Barium. Barium's an interesting one. It's not real dangerous. I mean, you know, not compared to some. 806 parts per million, that's okay. But it does cause muscle spasms, and because the most important muscle in your body, the heart, if you have enough barium poison, you can actually get a heart attack. So you can be that one. You guys having fun so far? Okay. All right. Chromium. Chromium is the thing that the weightlifters sometimes find in those pills that are not USDA approved. Helps you build muscles. Be careful though, because it also causes cancer and genetic damage, which means it'll not only kill you eventually, but it'll actually mess up future unborn versions of you. That's what the genetic damage there. So that's not a good one. We'll save this one for the, we'll save this one. There's some really bad. Oh, that one. Okay, let's do this one. Thallium. Thallium is radioactive, and it causes hair loss, gives you a skin on fire sensation, and also death. And it's only allowable at 9 parts per million. Can you hold 2, like your sister there? Is that, okay, good. We're doing okay now. Lead. Lead, really dangerous for children because it causes brain damage, but also in higher amounts, eventually death. Can you hold 3? Maybe under your chin, like this? Think that'll work? Okay. So normally I'd have like 8 or 9 kids, but they're all in school goofing around, not learning stuff like they would if they'd come to the Ranger program. Cadmium. Cadmium is 3 parts per million. Cancer, lung, kidney failure. You can also be cadmium. You can squeeze that in there. Yeah, you're doing very well. All right, and I think it'd be the yuckiest ones of them all. Okay, so we'll start with arsenic. Yeah, a poison, cancer and death. Mercury is kind of an interesting story because we used to measure the amount of mercury that came out of the coal plants, but not anymore. When they weakened the Clean Air Act back about 6 years ago, it was decided we don't need to measure mercury anymore. So we don't know for sure, but we know that any amount is too much. Mercury doesn't do any good for you, absolutely none whatsoever. But eventually, skin disease, kidney, lung failure, brain damage, and death. And then finally, the yuckiest of them all, uranium. Uranium, of course, very radioactive. Now, you can measure the amount of uranium comes out of a coal plant, even though it's not required by law. It's pretty easy. You get a Geiger counter. And what's been discovered time and time again over is that if you go to a nuclear power station that's 1 gigawatt, measure the radioactivity, go to a coal station that's 1 gigawatt, measure the radioactivity, 4 times more uranium from the coal station, which isn't measured and monitored at all, as opposed to the nuclear power plant. So these are the kinds of things that back millions of years ago, when these dinosaurs were here in a place like Bryce Canyon, those swampy wetlands, were being taken out of the environment. They were getting trapped in coal, and they would have stayed there forever. You know, volcanic eruptions, earthquakes, hurricanes, glaciers, none of that would have released these nasties back into the environment. It's only when we people dig up the coal and then burn it that all this heavy metal from millions of years worth ends up back in our lives. And that's why most of the coal plants are being heavily encouraged, let's say, to put on scrubbers to keep these kinds of things out of the environment. How about a round of applause for my heavy metal band? Okay, good job, you guys. You can go back to your seats. Now the next story is the story of our other rock, the limestone. And the limestone story begins much later in time, much more recent. And this is about 50 million years ago. The dinosaurs have long gone extinct. And what we have is the beginning of the Colorado Rocky Mountains forming right here, but also at the same time period, if you look closely, older mountain ranges, they don't exist anymore, but used to dominate the northern Utah-Nevada border, and an enormous mountain range is completely gone down here in southern Arizona. So all these mountain ranges trapped a basin in between. So as water and rain and then rivers flowed out of these mountains, it all went to this internal place right here and formed a lake. But a special kind of lake system, a lake that didn't have any rivers flowing out of it, just rivers flowing in. So what would happen is, because the main ingredient in most of these mountains was really ancient limestones, when the limestone dissolved, it would travel in the water to the lake, but as the water kept evaporating up into the sky, the concentration of dissolved limestone would increase. And you end up with a really thick limestone mud forming on the bottom of the lake, with iron mixed in to give it the pretty color. And that's how this story begins. The rest of it is that when the Colorado Plateau begins to rise, and this is probably about 20 million years ago, then it takes this low spot that once was a lake and it lifts it up high enough that the water drains out. And some of that water probably joined this newly forming Colorado River that used to go north but then reverses and goes through northern Arizona, cuts a big hole in the ground. Everybody thinks it's so grand. And then eventually makes its way out to the Pacific there. But the really interesting part was, once the lake was gone, all that mud at the bottom of the lake could become the beautiful limestone that you see here at Bryce. And as the Colorado Plateau continued to rise, it brought it up to a high enough elevation where the erosional forces are different. And what I mean by that is, it's kind of a little dark secret here at Bryce, but we're not really a canyon. Did they tell you that already? No? Good. Well, you should know. Yeah, why are we not a real canyon? There's one main ingredient you have to be a real canyon. Anybody know? A river. Yeah. And did you notice it's raining? Yeah, even when it's raining here, we don't have a river. Sometimes we get a little trickle of a creek down in the very bottom, but once the rain stops, it soaks in the ground. That's pretty much it. What's happening to Bryce is the freezing and thawing of water. This is what makes a pothole. But for obvious reasons, we don't call ourselves Bryce Pothole National Park. Remember how I said we're trying to get to 11 or 12% of Utah's visitation? Who would come to see a pothole, right? So let me see if I can demonstrate. Would you guys like to help me one more time? I need to show these folks how we make a hoodoo, and I'm going to use you guys as human hoodoos. And I promise I'll put all your body parts right back the way I found them, okay, when we're done. So we'll just kind of stand right here like this. Let's get shoulder to shoulder. All right, so you're going to pretend you're one of these fins of rock, these walls that jut out of the canyon here. And what causes you guys to form and to split apart is snow. So let's pretend it's October and the snow starts to fall. Not very much at first, but then we get into November and December and January. There's a fair amount of snow. Wow, this is a tough wall, by the way. There's like 100 pounds of force on top of it right now. There's a fair amount of snow built up by that time. And every single one of those days, from the beginning of about October, all the way around until almost June, we go above and below freeze in the course of every single day. So in the afternoon, when it's sunny, as it usually is, by the way, then in fact that snow melts and water trickles down inside the cracks, like right here between your shoulders. And then later at night, what do you suppose happens when that water freezes? That expands, right? It turns to ice, and it starts to force apart. No, not that much. You guys are wrong. Come on, get in here. You're tough. Yeah. And it starts to break apart little pieces bit by bit, and eventually, freezing and thawing day after night after day after night, over thousands of years maybe, we start to form, barely. Wow, you guys are tough. We start to form a little bit of a hole. There we go. Stop right there. Okay, we start to form a little bit of a hole, and even if they have some cap rock on top of them, if the hole gets big enough, go out just a little bit further, then the cap rock might not support itself, it crashes through, and here we have two beautiful, freestanding, odd-shaped pillars of rock from the forces of erosion that we call hoodoos. Thank you very much, ladies. Now, the rest of the story of Bryce Canyon is the story that's not always obvious to illustrate, but today is fantastic to talk about the chemical weathering of rainwater. Because in fact it does rain here from time to time. And what happens is when rain falls from the sky, it passes through carbon dioxide gas in the air and it creates carbonic acid. And carbonic acid does a number on limestone. It'll just plain dissolve it. But some of the rock out there, the cap rock that you'll see on top of the hoodoo's heads, like old Thor's hammer over there, he's got a nice big block of rock on his head. It's a different kind of limestone. It's the dolostone, dolomite, the dolostone that the gentleman mentioned. It has magnesium in it, and the magnesium makes it stronger. And so with that rain coming down on top, it'll just kind of trickle over to the edge and down the sides, and you think that those little droplets would have the decency to just fall right off, to respect gravity, mind their own business, this kind of thing. No, not little water droplets. Oh no, they have this annoying habit of sticking to one another and to the rock on the underside through the process of cohesion and adhesion. They stick to each other and they move their way and they get to the face, right, of the hoodoo. And this is the limestone, so they start to dissolve the face. They're just kind of melting the face year after year after year. And they give these hoodoos a skinny little neck. When you got a skinny little neck and a great big block of rock on top of your head here, your neck starts to get tired, right? But you can't nod your head, because if you nod your head just one time, down it all goes. And most of the time, the hoodoos just completely crumble into rubble. You wouldn't even know one stood there unless somebody had taken a picture. So that's the end story of hoodoos, the rain. But this brings us to a point of concern, because fortunately, rangers here at Bryce Canyon for many years have been taking pretty good climate recordings. Weather, rainfall, all that good stuff. And I've got 3 graphs to show you, but I'm just going to do it one at a time because it's a little bit easier to see what's happening. And so I've gone through all this data and worked out some interesting discoveries. What we've got here is the average high temperatures and the average low temperatures, the min, maxes, and means, as they like to say. And so this is taking the average temperature, the high temperature of every single day, adding them all up together, dividing by 365, and saying the average high temperature of that year was that data point right there. And if you look carefully at that red line, notice something kind of surprising. Notice how our high temperatures are actually decreasing. Huh? So clearly, global climate change is the greatest hoax ever performed on the American public. Unless you look at this line down here, because these are our low temperatures. And notice as we go back to 1945, our low temperatures here were about 24.5 degrees Fahrenheit, our average low. But now here in 2010, we're all the way up here at almost 29, almost 30 degrees Fahrenheit. Which means that in just 65 years, our average low temperatures have increased almost 5 degrees Fahrenheit, and that is a world record. Of all the climatic data that's ever been published, nobody can claim that great of change, which means we're number one. We're not happy about it. Especially when you take a look at some of these other bits of information. This is the number of freeze-thaw cycles. You remember when I was working on the freezing and thawing the ladies up here, making them into hoodoos? So this is the number of times a year, each day, we go above and below freezing. And back, as you see here, in 1945, we need to probably expose a little bit more. There we go. We had about 210 of these freeze-thaw cycles. But now, as we're up here in modern times, we end up with a lot less. Down here, instead of 210, we're here at about, 180 or 185. But the last part of our story, probably the most important part, is the precipitation. So take a look at this. What we've got is two different lines here. The top one with the huge amount of variability, that's inches of snowfall. And that's pretty typical. The snowfall changes a lot everywhere you go. But the bottom line is the overall amount of precipitation. That would be snow and rain added up together. So now when you look at this, you can see that our average snowfall was about 110 inches a year, and now we're up to about, what's this line here? About 80, 85 inches of snow. But notice how our water content hasn't changed. We still have the same amount of precipitation. So if we're having less snow, what are we getting more of? Rain. Yeah. Pretty easy to believe on a day like today. Did they tell you September is the sunniest month and you should plan your vacation for this time of year? It used to be true. Anyway, so these three things suggest that in the future of Bryce Canyon, and probably not our grandchildren, maybe not even these ladies' grandchildren, but if things continue the way they're going, somebody's going to see a very different Bryce Canyon. Instead of great big tall frost-wedged hoodoos, we're going to see these shorter, conical, dumpy, rain-eroded ones. And you think we'd get $25 a carload, to see? Maybe not. I mean, depends what inflation does, right? But probably not. My point is that, of all the things we'd have to worry about when it comes to global climate change, I can think of like a billion, roughly. I can think of a billion that are more important than the rocks of Bryce Canyon. But it's interesting to think that we are a species who lives on a planet where we can actually change the geology of the planet if we're not careful. And hopefully with that in mind, it'll give you an opportunity, reason to reevaluate some of this information and see if you can't draw some new conclusions. Now, the story in this area is also confounded by the amount of coal, not that we mine, but the amount of coal that we burn. So here's the Four Corners map one more time, and you can see 27 different coal-fired electric plants in this region. Most of them are in Utah. And, well, some of them have scrubbers and take out some of those nasties we talked about before. All of them are releasing huge amounts of carbon dioxide, which means that our air immediately over us has more carbon dioxide than most places you would travel. So as the rain comes down through here, even what little amount we get, it has more carbonic acid than you might experience. And the coal is primarily, in this modern world, used to power electricity. Here's North America at night. Lots and lots of lights, probably more than we really need. And so the solution to this problem is being a little bit more careful with our electricity use. But before we go into that, I want you to understand that coal has served a very important ecological role in the history of our planet because it saved us from the first climate crisis. Anybody familiar with the first climate crisis? We don't talk about it much. Boy, it was a doozy. Okay. What's that? Oh, after the Ice Age. These years here, is it written there? It is from about 1500 to 1850, we as humans nearly deforested the entire planet. When you look at this map, you'll see green being forests we didn't cut down, but the gray is the forest we did cut down. Take a look at Europe. Take a look at Southeast Asia. In those 300, 350 years, we just about clear-cut those regions to the ground. Why? Well, we needed wood to create fires, to keep ourselves warm, to cook our food, well, of course, to build our homes, to build sailing ships. So we could sail across vast new oceans, discover new continents with new forests, cut those down, and make more sailing ships so we could sail back to sail forward to cut more trees to... And then eventually somebody said, several somebodies actually, you know that black rock that makes your hands really dirty? It's kind of gross, and it's hard to dig out of the ground, makes your back tired. I mean, it's way harder than cutting down trees. But you know what? If you get your fire hot enough, this stuff produces a heck of a lot of energy. And pretty soon, with coal as our salvation, we didn't have to use nearly as much wood. We didn't have to use it for fires. We didn't have to use it for homes. We didn't have to live in wood homes anymore. We could start building masonry, all kinds of neat stuff with the energy from coal. And of course, our ships could then become iron and eventually steel because of the power that coal provided us. And that's just the beginning of the story. Think about us as the National Park Service. Okay? We wouldn't be here if it wasn't for the railroad industry, and the railroad industry wouldn't have been there if it wasn't for coal. You know, the railroads were the first people that were going to support the national parks. They were going to take a chance on a crazy idea. What? Set aside land that nobody really owns, but everybody can enjoy? Is there money in that? And people said, yeah, a little bit. And the railroad said, okay, well, we'll give it a try. And here we are as the National Park Service system. Coal is what made or helped us win World War I, World War II. Because we had good coal reserves, which means we could make stronger steel than our enemies, and that was a key strategic path to victory. And of course, in this modern world, as I already said, coal is providing with huge amounts of electricity, not just out in the United States, but for the most part around the globe, coal is the main source of electricity. Now, the good news is that there's lots of different ways to generate electricity. Kind of hard to get a look at all these different things here, but if you want to come up later and look at them more closely, you're welcome to. But we have all kinds of ideas, not just solar and wind, but geothermal, tidal actions, combinations of the above. There's different ways to generate electricity. But people will say, they'll say, yeah, but the technology's not proven, you got the storage problem. That's like that guy that kept telling everybody else, don't stick the coal in your fireplace, it makes your hands dirty, it's hard to dig out of the ground. But eventually they figured it out, and so can we. But probably most of you, like me, probably don't have a few $100 million or $1 billion capital laying around to invest in a green energy electric generating station. I'm just guessing. If you do, see me after the show. These are the ones we want at Bryce right here, and we'll splatter your name all over them, you know, to be able to give you some good billing there. But at any rate, what we all can do is we can conserve electricity. And people say to me, well, you know what, Ranger Poe, I'm an American, and I enjoy my freedoms. I enjoy the freedom to own a 3,000-watt hot tub. It's the perfect place to sit when I'm watching my 500-watt plasma screen television. Okay, you know, I enjoy my freedoms too. I maybe love my planet a little bit more, but we don't have to change our lives to make a huge impact on reducing our amount of electricity, reducing our carbon footprint, because there's some neat solutions that everybody can do pretty easily. The one I always am talking about are the light bulbs. So here I've got different kinds of light bulbs. This is the one that Thomas Edison invented about 134 years ago. I think the greatest invention of our entire species. I can argue for hours, if you would like, to indulge me, about how everything significant that came afterward all can be traced back to this. But in 134 years, we haven't done much different with this. It's the same technology. Anybody else have anything in your house, 134-year-old technology? Your car? Well, no, we didn't have cars. Your computer? I don't know. Pencils? Shovels, maybe? Okay. Well, this is not the most efficient use of electricity because it would take about 700 pounds of Utah coal to power this for 24 hours for an entire year. Nobody would leave a light bulb on like that. That'd be ridiculous, but let's just play along. 24 hours, entire year, 700 pounds of Utah coal. Now, the newer technology has been refined quite a bit in the last 30 years. Fluorescent light bulbs. Fluorescent light bulbs, 175 pounds of coal. But then people say, yeah, but they contain mercury. Okay, yes, but they contain mercury. Contain is the key word. Unless you break this, the mercury is safely inside of this. When you take it to a recycling center, they're going to manage the mercury vapor. You don't have to worry about it. Only 175 pounds of coal to 700. But if you don't like the mercury, you don't want to subsidize mercury industry, great. Because the next step you can do is the LED light bulbs. And these are fantastic. Same amount, 100 watts, but instead of 700, 175, 50 pounds of of high-quality Utah coal to light this. And they come in all different colors now. You can get the natural sunlight, if anybody remembers what that looks like. And you can get the yellow one if you want to have like the campfire light, like the incandescents. You can get the blue light if for some reason you like the fluorescent lights. It's all right here. And the neat thing about these light bulbs, last for a long time. This costs $1, lasts for a year, barely, if you left it on 24 hours. 24 hours a day. This one costing $2 would last about 5 years. This one costing $16, but would last 25 years. Now the very best thing about the LED light bulb is it's almost indestructible. And I don't want to give anybody a heart attack here, but I'm going to drop this on the asphalt just to show you how tough these things are. They design them that way because, you know, let's face it, you're going to spend $16 for a light bulb. You want to know that you're going to get something very durable and you don't accidentally ruin your investment if you drop it on the ground. They say you can actually drop these from 6 feet, but I haven't quite got that confident yet. Nevertheless, they are very durable. So hopefully they will become the future, and a good future, maybe even a brighter future, you might say. Good for your future finances, but also very good for the future of a place, well, like Bryce Canyon. Now, the tale of two rocks. The geologic portion of the story, the history, has already been decided. In fact, it's quite literally set in stone. The coal and the limestone of Bryce that everybody comes to see. But the good news about being a species where we can actually change the geology of the planet we're living upon is we can decide how we're going to write the future of the tale of two rocks. We're going to use more of the coal. We're going to try harder to save more of the rock of Bryce Canyon. My name is Ranger Poe, and don't forget to turn off the lights when you leave. Thanks.